Okay, so for the sake of those persons, um, hold on, let me see here. Hold on, let me go back to sharing. And let me see, is there a way of okay, I thought I could get back what I wrote. Okay, so any questions, as I said? Hold on, let me see here. Somebody. Oh, thank you. Yes. Okay, so the next question is question number 8. And in question number 8, it says a gaseous reaction mixture contains SO2, Cl2, and SO2, Cl2, and it gives you the different pressures of the different gases in a 2.0 liter container. It gives the Kp for the system, and then it says, and it gives you the equation, and the question is asking, is the above system at equilibrium? So that's the first question. Is the above system with those values for the pressures at equilibrium? Now, if you remember, we said, turn on my writing here. We said that at equilibrium, the QP in this case would be equal to KP, right? So they gave you the KP value already, which is 0.011. So the question is the system at equilibrium? In other words, we have to find QP based on the numbers given. So QP would be equal to the concentration of SO2 times the concentration of Cl2 divided by, okay, I'm already messing up. This should be pressures, not concentrations. So this should be the pressure of SO2 times the pressure of Cl2 divided by the pressure of SO2 Cl2, right? And then we put the numbers in. So for SO2, it is 0.30 atmospheres multiplied by 0.16 atmospheres divided by SO2 Cl2 pressure, which is 0.50 atmospheres. And when I did that calculation, I got 9.6 times 10 to the minus 2. And by the way, please verify these answers because, of course, I could be wrong. So please feel free to correct me if I've made a mistake. But this is what I got, right? I got 9.6 times 10 to the minus 2. So what we do next is compare 9.6 times 10 to the minus 2 to the Kp value, which is 0.011. And we can see clearly that the 9.6 times 10 to the minus 2 would be greater than 0.011. So therefore, because it's not equal, right, the QP is not equal to the KP, that means that the system is not at equilibrium, all right, because the QP is not equal to the KP. So the question is asking in the B part, if the system is not at equilibrium, which it is not, in which direction will the system move to equilibrium, right? Now, in this case, we know that QP is greater than KP, right? So basically, you need the system to shift in such a direction such that the QP would be reduced, right? So what that means, therefore, is that the system will shift in the direction shown here to the left so as to reduce the pressures of SO2 and Cl2 and to increase the pressure of SO2, Cl2, and therefore the QP would be lowered such that it becomes equal to the KP. So the answer here is that it's going to shift to the left in order to achieve equilibrium so that QP will now be equal to Kp. All right? So that's the answer for the B part. Okay, any questions so far? Any questions about what we have just done in this question? Any questions? All right, so let me, because I'm going to need space, let me clear this. And scroll down. So the next question is, what will be the concentration of SO2? Hold on, wait a minute. Did I skip something? Okay. What would be the concentration of SO2, Cl2 when the system achieves equilibrium? All right. So again, this will be a kind of ice table type of problem. The only difference now is that instead of concentration values, you're going to use pressure values. So I'm going to rewrite the equation here, which would be SO2, Cl2 to form SO2 plus Cl2. And I'm going to write down the initial pressure values, which for SO2 is 0.50. SO2 Cl2 is 0.50. For SO2, it's 0.30. And for Cl2, it is 0.16. Right? So as we said before, the system is going to shift to the left in order to achieve equilibrium. So what that means is that some of the SO2 will react with some of the Cl2 to form some of the SO2 Cl2, right? So we don't know what the amount of SO2 or Cl2 that will react. So I'm just going to say X, I'm going to let X equals to the pressure of SO2 that reacts, right? So if that's the case, I'm going to put minus X here, which will be the change in SO2. And because of the 1-to-1 mole ratio between the SO2 and Cl2, this is going to be minus X as well. And then as far as the SO2, Cl2 is concerned, that's going to be plus X, all right? And then at equilibrium now, you're going to have 0.50 plus X. Here, it will be 0.30 minus X. Here, you're going to have 0.16 minus X, right? So therefore, we can put these terms into the Kp expression. Kp would be equal to the pressure of SO2 times the pressure of Cl2 divided by the pressure of SO2 Cl2. And then you put the numbers in. So I'm going to continue down here. So Kp would be equal to 0.30 minus X times 0.16 minus X. And then below here, I'm going to put 0.50 plus X down here, right? And that would be equal to the Kp value, which was given as being equal to 0.011, right? Now, I'm going to skip some steps here because basically it's all algebra from here because the aim is to find out what X is, right? So I'm going to skip, I'm just going to say several steps, right? And I'm going to give you what I determined to be the value of X. So when I solve for X based on this equation, the value of X, actually, there are two values of X that you're going to end up with because if you work it, if you go through all the steps, you're going to end up with a quadratic equation, right? So the two values of X that I ended up with, one is 0.35 and the other one is 0.12. And between these two, only one of them would be valid, right? And how do you determine which one is valid? Well, it's quite simple. If you recognize that these values here must be positive because there can be no such thing as a negative pressure, right? So what that means, therefore, is that X must be less than 0.16, right? So therefore, the value of X that you're going to use out of these two would be 0.12, all right? So therefore, we can say that X, we can cross this out and say X is equal to 0.12. Now, remember what the question is asking for. The question is asking for the concentration of SO2 Cl2. So what we would have to do now is find out what the pressure of SO2 Cl2 is based on the X value that we just solved for. So the pressure of SO2 Cl2 would be 0.50 plus X, which is 0.12 atmospheres, right? Atmospheres. So this works out to be equal to 0.62 atmospheres, right? Okay, but we're not finished because the question is asking for the concentration. Let me just erase the top part here since I'm going to need the space. the question is asking for the concentration of SO2. What we have found so far is the pressure of SO2. So the question now becomes, how do we get the concentration based on the pressure? And it goes back to the ideal gas equation, or a form of it. PV is equal to nRT, remember that? From your Chem 1. Well, we can rearrange this to get P is equal to N over V times RT, and N over V would be equal to the concentration of SO2 Cl2, right? And P is this will be the pressure of SO2 Cl2. So to get the concentration of SO2 Cl2, we divide the pressure of SO2 Cl2 by RT, R being equal to 0.08. Well, I'm sorry, let me just put RT here. So let me put RT here and then put the numbers in. So the pressure of SO2 Cl2 we worked out to be equal to 0.62 atmospheres divided by R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is, from the top of the question, 300 Kelvin. All right, and then we work that out. So I did that myself, and I got 0.025 M, right? Atmospheres will cancel out, the Kelvin will cancel out, so you're going to end up with mole per liter, which is the same thing as M. And that's how that is done. All right? Okay, any questions about this one? Any questions? Any questions out there in Zoom? Before I forget, let me capture those persons who just joined us. What's your name again, sir? Last name? Laparda. Okay. And ma'am, your name? Victoria. Victoria Mendez. Okay, all right. And I don't know if anybody else out there in Zoom joined us late. Let me see here. Let me go back to Aleo is not here. Okay, everybody else is here. All right. Okay. So let me go back to share my screen. And we're going to move on to the next question, which is question number 9. Let me scroll down. Okay, so question number 9, they gave you the system at equilibrium, right? And they gave you the initial concentration of PCl5, and the question is asking for you to calculate the concentrations of everything at equilibrium, all right? So this is another ice table. Oh, and they gave you the Kc as well, right? So this is one of those ice table type of problems. In fact, this is the first line in the ice table, the initial values. So it's kind of similar to the one we did before this one, where we don't know what the equilibrium concentrations are. So what I'm going to do now is create another line here, which says change. All right, and the change here would be, well, the reaction would have to shift in this direction because you're going to need some product in order for the equilibrium to be achieved. So therefore, we know that the change as far as the PCl5 would be negative. So we're going to call that negative X. Here we're going to have plus X, and here we're going to have plus X. And of course, we know these will be plus X in each case because of the stoichiometry of the equation. So at equilibrium, you're going to have 1.00 minus X. Here you're going to have X, and here you're going to have X. So therefore, Kc would be equal to the concentration of PCl3 times the concentration of Cl2, all divided by the concentration of PCl5, all right? So that would be X squared over 1.00 minus X, and that would be equal to the Kc value, which is 0.0013, right? And then now, again, I'm going to skip all the steps that I went through. Basically, you're going to end up with a quadratic equation where X squared plus 0.0013 x minus 0.0013, and that will be equal to 0. And when I solve for x, I got x being equal to 0.035, all right? So that's what x is. So once you find out what x is, then you can easily find out what the concentration of PCl5 is, PCl3, and Cl2. In fact, the concentration of PCl3 would be equal to the concentration of Cl2, which would be equal to x, which is 0.035 m, right? And then as far as the concentration of PCl5 is concerned, that would be equal to 1.00 minus 0.035. And when I worked that out, I got 0.097. Rounded off to 2 decimal places, 0.09. I'm sorry, 0.97. 0.97. 0.97 m. And that's how that is done. All right? Okay, any questions about this one? Any questions? Any questions? No questions? All right, and I think that is the end of assignment number 3. So what I'm going to do now is create a Dropbox for that. Let me clear this here. So let me go to assignments and assignment number 3. Let me go here and okay, so today is the 2nd of March. Oops. So I'm just going to let it be due on the 4th, day after tomorrow. So let me go here. It's available from today until the 4th. And I'm going to save that. Okay, so now you'll be able to upload your assignment into that Dropbox that I've just created. All right. So with that said, we're going to move on to the next chapter because I remember telling you guys to watch the videos for chapter 4. So this is the assignment that we're going to work on right now. So let me share. Oh, what am I doing? I'm already sharing. Okay. So for you guys, oh, by the way, did I publish this? Let me see if I publish this for you guys out there in Zoom. Assignment number 4. Oh, no, I didn't. Okay, so let me publish that now for you guys out there in Zoom. And for you guys here, let me give you a hard copy of this assignment. So chapter 4 deals with acids and bases. And in your Chem 1 classes, you should have been introduced to what an acid is and what a base is. We're going to get into it in more detail in terms of different definitions of acids and bases. Because one of the things you're going to learn in this chapter is that there are actually different definitions of acids and bases. And not only that, but you're going to learn about some quantitative relationships, measurements, and so on, dealing with acids and bases. You'll be introduced to terms that you've probably heard before, like pH, which is a scale that is used to measure the level of acidity of aqueous solutions and so on. So a good number of things that you're going to learn in this chapter, all right? Or you should have learned if you watch the videos, right? So the first thing we're going to talk about is in the first question, which talks about, let me make this full screen. Okay, so the first question is testing your understanding of the terms acid, base, conjugate acid, and conjugate base. So basically, one definition of an acid that is most widely used, I would say, is that an acid is a substance which loses hydrogen ions to a base, right? And a base is a substance which accepts hydrogen ions from an acid, all right? Now, that's the definition of an acid and base consecutively, right? Now, the thing is, when an acid loses a hydrogen ion, the species that is formed is called a conjugate acid, right? And when a base gains a hydrogen ion, the resulting species that is formed is called a conjugate acid, all right? So in answer to the first question, you have to look at what transformation is taking place, right? If you look at the first one, turn on my pen here, you'll see that as you go from left to right, okay, what's going on with this here? Okay, as you go from left to right of this equation, you'll see that H2SO4 loses a hydrogen ion, right, to form HSO4 minus. So therefore, H2SO4 would be the acid, right? And the hydrogen ion that is lost from the H2SO4 is transferred to the nitrogen of the ammonia to form the ammonium ion. So this would be the base. Oops, sorry. This would be the base, all right? So on the other side of the equation is where you'll have what is known as the conjugate base. The conjugate base is what is formed when the acid loses a hydrogen ion. So the HSO4 minus would be the conjugate base, right? While the NH4 plus, which results from the ammonia gaining a hydrogen ion, so this would be the conjugate acid, and that's it, all right? So that's how you can determine what's an acid, what's a base, what's a conjugate base, what's a conjugate acid, right? So just to reiterate this point, the acid is a substance that loses a hydrogen ion to a base, while a base is a substance which gains a hydrogen ion from the acid. When an acid loses a hydrogen ion, it forms a conjugate base. When a base gains a hydrogen ion, it forms a conjugate acid, all right? So with that said, let's look at B, and let me hear what you have to say about B. Look carefully at what's happening as you go from left to right, and I want you to tell me what's an acid and what's a base. Let's deal with that first. So what would be the acid in this case? I'm sorry?
HCl.
H what?
HCl. Or 3. Which one are we? Oh,
We're looking at this one.
Oh, the acid would be HC2.
Right, so this would be the acid. And I think, let me see, somebody's saying something in the chat. Okay, yes, Mr. David is agreeing with us. All right. And what would be the base? Well, obviously the base would be the water, right? Okay, so what would be the conjugate base on the other side? I'm sorry?
The C2H3.
Exactly. So this would be the conjugate base, and this would be the conjugate acid. All right? Okay, now the next one is a bit tricky, slightly, but the same principle applies. All right, so I want you to look at it and tell me what's acid in C.
HCl.
Mm-hmm. Which means that this would be the base, right? So what would be the conjugate base? Exactly. And to be technically true, it's actually the chloride, but because it's combined with the sodium, we're just going to say this would be the conjugate base, which would mean that this would be the conjugate acid. And that's it. Okay, very good. Let me clear this here. So if you understood what we just talked about here, then number 2 should be a breeze. In fact, number 2 and 3 should be easy, all right? In the case of number 2, it's asking for you to give the conjugate base of each of the following acids, right? And by the way, the definition that I mentioned before is called the Bronsted-Lowry definition, right? Of acids and bases, right? According to Bronsted-Lowry, an acid is a substance which gives up a proton to the base while a base accepts a proton from the acid. All right, so this question is asking for you to give the conjugate base in each of these, for each of these acids, right? So what would be, in your opinion, the conjugate base in the case of A? What is formed, in other words, when it loses a proton or H plus ion? I what? I minus, exactly. What about B? NH3. What about C? HCO3 minus. And what about D? NO3 minus. Okay, very good. And then in the case of number 3, they're asking for the conjugate acid of each of these. So let's start off with A. What's the conjugate acid? HCN. Okay, what's the conjugate acid in this case? HO minus. What's the conjugate acid in this case? Or, well, that's one way of doing it. In fact, let me just leave it like that. Even though technically when it comes to organic acid, we put the hydrogen here, but I'll accept that for now. Okay, let me see here. Is that it? Oh, one more. Let me clear this here. What's the conjugate acid in the case of D? NH4 what? Plus, exactly. All right, very good. So let me clear that. Let me scroll down. Okay, so this question is asking, what is the pH of a solution that contains 25 grams of hydrochloric acid dissolved in 1.5 liters of water? Now, if you're asked to determine the pH of any solution that contains an acid or base, the first thing that you have to ask yourself is whether or not the acid or base is strong. Now, I don't think I've had any of you in my Chem 1 class, but I know that there are a couple of students out there in Zoom. Let me see. You know, people like, let me see here. Afra Anwar, Mr. Ranley. I know those two were in my Chem 1 class. And they should be able to tell me what the 6 strong acids are. Who shall I pick up? Should I pick on Miss Anwar or Mr. Ranley? I'm going to pick on Mr. Ranley. Mr. Ranley, can you hear me? Don't pretend as if you don't. Okay, so Mr. Ranley, can you tell us what the 6 strong acids are that you need to memorize, that I have told you last semester that you need to memorize? 6 strong acids. Oh, and Miss Afreen Anwar is there as well. She, I used to have her as well. I don't remember if Miss Pilgrim was in my class. Miss Pilgrim, were you in my Chem 1 class? Oh, yes, you were. So you should be able to tell me also. But let me hear what Mr. Ranley has to say. Hold on, let me check the text. Okay. Hydrochloric, hydroiodic, hydrobromic, nitric. Okay, so you have 2 more. Anybody want to help him out? He's right so far in terms of 1, 2, 3, 4, right? There are 2 more strong acids. Sulfuric and perchloric, exactly, right? So as I told those students in my Chem 1 class, and I'm telling you now, you need to memorize these 6 acids as strong acids, right? Hydrochloric, hydroiodic, hydrobromic, nitric, sulfuric, and perchloric, right? Those are strong acids, right? So if you see any questions involving strong acids, involving any one of these, you can assume that it's a strong acid. And of course, you should know what it means. When an acid is strong, it undergoes complete dissociation, right? Pretty much all other acids that you're going to meet, unless you're told otherwise, will be weak. In other words, those acids will undergo partial dissociation. So it's very important that when you read a question like the one that we just looked at, let me go back to share my screen. The first thing you have to ask yourself is, what type of acid is it? Is it a strong acid or a weak acid? Now, in this case, it's a strong acid. Hydrochloric acid is one of the 6 strong acids, right? Now, another thing I need to talk about here, which was covered in the videos, is the concept of pH, right? And there's a formula which relates the pH of an acid solution to the concentration of H plus. The pH is equal to minus log the concentration of H plus. Or another way of writing it is minus log the concentration of H0 plus, which is actually a more realistic representation of what actually happens in water. Even though you can still use this in order to express the concentration of H plus, but in actual fact, the H plus will combine with water to form this, which is known as a hydronium ion, all right? So when the question says, what is the pH of a solution that contains 25 grams of HCl dissolved in 1.5 liters of water? The first thing I would do is try to find the concentration of HCl. So the concentration of HCl would be equal to the moles of HCl, but first you have to convert the 25 grams of HCl to moles. So you're going to put 1 mole here, and the molar mass of HCl, of course, by now you know me, I'm lazy, so I'm just going to look up the molar mass or use my molar mass calculator. Okay, so HCl and the molar mass is 36.46. So that will go down here. So this would be 36.46 grams, all right? Okay, so that would give you the moles, and then you'd have to divide that by the volume of the solution in liters. And the volume, according to the question, is 1.5 liters. So I'm just going to divide that by 1.5 liters, and that will give you the molarity of the HCl. And according to my calculations, and again, please check to make sure I'm doing the right calculation, but according to my calculation, this works out to be equal to 0.46 m, all right? Now, because we know that hydrochloric acid is a strong acid, we know that it undergoes complete dissociation to form HCl, I'm sorry, H plus and Cl minus. So therefore, the concentration of H plus will be equal to the initial concentration of HCl. So therefore, this will be equal to the concentration of H plus. So we can say that the pH is equal to minus log of 0.46. And according to my calculations, this works out to be 0.34 as the pH of that solution. And that's how you do that. All right? Okay, any questions about this one? Any questions? Any questions? Right, there's no units associated with pH. It's just the number, 0.34. Yeah. Okay, so if you understood what we just did in 4, then you should be able to do number 5. I'm going to leave that for you guys to do. Basically, it's the same thing. The only difference is that the mass is different and the acid is different, but it's a strong acid. Nitric acid is one of the 6 strong acids, right? And the volume is different. They gave it a volume in milliliters. So in that case, you have to convert it to liters before you do the rest of the calculation, all right? So I'm going to leave that for you guys to do. Of course, if you encounter any difficulty doing this particular question, then please feel free to contact me concerning that, all right? So I'm going to scroll down to the next question, which is number 6. Now, let me see if you can tell me what you do in this case. In this case, the question is asking for a pH that contains 2 acids. One of them is nitric acid, and it gives you the amount of moles, 1.2. And the other is hydrochloric acid, and they give you the moles of that. And it says that it dissolves in 1,000 liters of water, right? So, how would you tackle this problem? Let me hear your ideas. And you guys out there in Zoom, feel free to chime in. How would you solve this particular problem? They gave you the 2 acids and their mole values, and the solution, the total volume of the solution is 1,000 liters. Remember, the first thing you should ask yourself, is the acid strong or weak? Or in this case, the acids, there are 2 of them. Are they strong or weak? They're both strong, all right? So we can conclude what? I'm sorry? Exactly. So both nitric acid and the hydrochloric acid will dissociate, all right? So how does that help in terms of calculating the pH? Exactly. So how would you calculate that? Okay. So you're saying divide 1.2 moles divided by 1,000 liters. Okay. So this gives a total of 2.9 moles divided by 1,000 liters. So that would be 0.0, that would be 2.9 times 10 to the minus 3 m, right? Okay, what next? Exactly. So pH would be equal to minus log of 2.9 times 10 to the minus 3. And when I did that calculation, I got, okay, I got 2.54. All right. And let me just say something here, which I probably should have stressed in the previous problem. When it comes to rounding off your answer to the correct number of sig figs, right? There's a certain rule you need to follow, and that is this. Whatever the number of sig figs that you have here that you're finding the log of, that should be equal to the number of decimal places here, right? So in this case, we have 2 sig figs here, which means that once you do your thing on your calculator, find the minus log of 2.9 times 10 to the minus 3, you round off your answer to 2 decimal places, right? So whatever the number of sig figs in the number that you're finding the log of, you round off your final answer to the number of decimal places, the same number of decimal places. All right. Okay. Any questions about this one? Any questions? Exactly. Whenever you find the log of something, whatever the number of sig figs in the number that you're finding the log of, then in your answer, you need to round off to that number of decimal places. All right. Okay. Any other questions? Any questions out there in Zoom? Okay. Number 7 says, if a solution has a hydrogen ion concentration of 4.5 times 10 to the minus 7, is this an acidic or basic solution? Now, what this has to do with is the relationship between the concentration of H plus and the concentration of OH minus in any solution, any aqueous solution, I should say. That product is always going to be equal to 1.0 times 10 to the minus 14. And this is called the ionic product of water, Kw, right? Kw is called the ionic product. And this is based on what is called autoionization. Let me just quickly go through that. So H2O, if you get any pure sample of water, what you'll find is that it's going to dissociate to form H plus and OH minus, right? So because this is a system in equilibrium, the same equilibrium equation that we learned in the previous chapter will apply here. So this is the equilibrium equation. Kw is equal to concentration of H plus times the concentration of OH minus, right? Another thing I should mention here, the state symbols are kind of important. This is aqueous, but this is liquid. And I think I covered this in the videos for the previous chapter. If you have a system in equilibrium where you have something existing in a liquid state or in a solid state, then you would not include them in your equilibrium expression like this, all right? And I won't go through the reason why that's the case, I won't go into it in detail. I think I covered that in detail in the video, but the reason why is that if you have a solid or liquid present in the equilibrium system, their concentration doesn't change. The only thing that will change in their concentration are those substances that are in the aqueous state or in the gaseous state, all right? So that's why you see in this particular equation here, there's no H2O concentration term in this equation, right? Now, this is true for any aqueous solution, true for any aqueous solution. So it doesn't matter what is in the solution, right? The product of the concentration of H plus and OH minus is going to be equal to a constant value of 1.0 times 10 to the minus 14. And by the way, this is temperature dependent. In this case, the temperature is 25 degrees Celsius, right? So you'll find that the Kw value will change according to temperature. But for most intents and purposes, for example, for the calculations that we're going to do involving aqueous solution, we can assume that the temperature is 25 degrees. So with all that said, the question says, if a solution has a concentration of H plus of 4.5 times 10 to the minus 7, is this an acidic or basic solution? Now, let me just say that an acidic solution, the concentration of H plus is greater than the concentration of OH minus, right? In a basic solution, the reverse is true. The concentration of H plus is less than the concentration of OH minus. And in a neutral solution, the concentration of H plus is equal to the concentration of OH minus. All right? So, what do you think the answer to this question is? If the concentration of H plus is this, 4.5 times 10 to the minus 7, is this solution acidic or basic? Acidic. And the reason why it's acidic is because exactly. So let me create some space here. So if you were to find the concentration of the concentration of OH minus would be equal to Kw divided by the concentration of H plus. That'll be 1.0 times 10 to the minus 14 divided by 4.5 times 10 to the minus 7. And what does that give? I didn't do the calculation for it. What
3.2 times.
Okay, right. So therefore, the concentration of OH minus is definitely, excuse me, less than the concentration of OH minus. So therefore, solution is acidic. Another way of doing this, which is probably easier, is to recognize that, as I said before, for a neutral solution, these two are equal, right? And in order for the solution to be neutral, that means that the concentration of H plus must be equal to 1.0 times 10 to the minus 7, right? M. So that would be equal to the concentration of OH minus. So one could say that because 4.5 times 10 to the minus 7, M, is greater than 1.0 times 10 to the minus 7, M, again, that means that the solution is acidic. So that's just an alternative way of coming to the same result. Okay. Any questions about this one? Any questions? Okay, let's clear this and scroll down. Okay. I'm going to leave number 6 for you to do. You should be able to do number 6. It's a dilution. It's a combination of pH plus dilution. Again, if you have any issues doing that problem, let me know. Okay. And let me see here. Okay, so let's look at question number 7. It's asking for the pH of the following solution. So again, you have to ask yourself if the resulting solution is of a strong acid or strong base. So HBr, of course, is a strong acid. So therefore, that means that it undergoes complete dissociation, which means that the concentration of HBr would be equal to the concentration of H plus. And we are given that the concentration of HBr is 4.5 times 10 to the minus 3 M, right? So therefore, the pH is equal to minus log of 4.5 times 10 to the minus 3. So I think I did that problem. Let's see here. Okay, so the answer I got when I did that is 2.35. And that's it. All right. So that's relatively easy. Yes, sir.
On the last one, it was 2.2 times 10 to the negative 8, that's on me.
I'm sorry?
It was 10 to the negative 8, not 10 to the negative 22. I typed it in wrong.
Oh, you mean for the previous one?
But the-
Oh,
It
okay.
doesn't change the answer.
Right, okay.
But just,
So it's what?
it was 2.2 times 10 to the negative 8.
Oh, 2.2 times 10 to the minus 8. Okay.
Yeah, but that doesn't change it.
Yeah, all right, good. Okay. Now for the B part, they're asking for the pH of this solution, right? Oh, by the way, this is something again that should have been covered, well, was covered in the videos. Let me just remind you. So remember I said that Kw is equal to the concentration of H plus times the concentration of OH minus, right? Which is equal to 1.0 times 10 to the minus 14, all right? Now, we know that the pH by definition is minus log of the concentration of H plus, and there's another term known as a POH, which is minus log the concentration of OH minus, right? Now, if you imagine, and this is where some algebra will come in, if you do the log of both sides of this equation, you're going to end up with log of the concentration of H plus times concentration of OH minus, and I should say minus log, and that will be equal to minus log of Kw, right? Now, you should know from your algebra that this part here would be equal to minus log of the concentration of H plus minus log of the concentration of OH minus. And that would be, oops, OH minus. And that would be equal to minus log of Kw, right? This part here would be equal to the pH. This term here would be equal to the POH. And when you add those two, you're going to get pKw, right? Which is minus log of Kw, right? And minus log of Kw is going to be equal to 14.00, right? So basically the sum of the pH and the POH of any solution is going to be equal to 14.00, all right? That will become important later on, not in this question here, I think, but later on. But I just thought I should review that so that you know how to apply these relationships to solving some of the problems that you're going to encounter later. All right, now let's go back to B. Let me clear this here. Now in the case of B, they gave you the molarity of a potassium hydroxide solution, 3.67 times 10 to the minus 5, right? So potassium hydroxide is a strong base. And again, for those of you who had me before in Chem 1, you should remember that the strong bases are basically the hydroxides of groups 1A and 2A, all right? So like potassium hydroxide, sodium hydroxide, lithium hydroxide, calcium hydroxide, magnesium hydroxide, all of those are strong bases, right? So in this case, potassium hydroxide is a strong base. So we know that the concentration of KOH is equal to the concentration of OH minus because it's a strong base. So that will be equal to 3.67 times 10 to the minus 5 M. So that means we can find the POH. So the POH is equal to minus log of 3.67 times 10 to the minus 5, right? And I did that and I got 4.44, right? But the question is not asking for the pH, the question is asking for the POH. I'm sorry, the question is not asking for the POH, it's asking for the pH, right? And we know that when you add the pH to the POH, that's equal to 14.00. So therefore we can say that the pH is equal to 14.00 minus the pH, which is 4.44, which works out to be equal to 9.56. And that's how that is done. All right? Any questions about this one? Any questions? Okay. Any questions out there in Zoom? Okay, in the case of C, it says a solution is made by diluting 25 mL of 6.0 m hydrochloric acid until the final volume of the solution is 1.75 liters. So you're asked to find the pH of that solution. So this is a dilution problem. And of course, I'm quite sure you have met this equation. C1 V1 is equal to C2 V2, right? That's a dilution equation, right? So basically, they gave you V1, which is 25 mils. They gave you C1, which is 6.0 m, and they gave you V2, right, which is 1.75 liters. So the aim is to find C2. So we can rearrange this equation to get C2 is equal to C1 V1 over V2. So we're going to put the numbers in. 6.0 m would be C1 times V1, which is 25 mils, divided by V2, which is 1.75 liters. Now, in this case here, in order to solve this problem, you need to either convert the 25 mils to liters or the 1.75 liters to milliliters. It doesn't matter which one you do. So I'm just going to do this here. I'm going to convert the liters to milliliters, which means that you're going to have 1 liter down here and 1,000 mils above. And then we work this out. Let me see, did I do that? Okay, so when I did that, I got 0.086 m. All right, so that would be the concentration of the hydrochloric acid. Now again, hydrochloric acid is a strong acid, so the concentration of HCl would be equal to the concentration of H plus, which is the 0.086 m. So therefore the pH would be equal to minus log of 0.086. And according to my calculations, that works out to be equal to, and again, check to make sure I'm doing the right thing, but I got 1.07 as the resulting pH. All right. Okay, any questions about this? Any questions? Any questions? Any questions? Okay, let me see here. Let me clear this and scroll down. Okay, now in the case of B, I'm going to leave that for you to do on your own. Basically, you're given the mass of HBr, the mass of nitric acid, and you're given the total volume of the solution, the resulting solution, and you're asked to find the pH, right? So try that on your own. If you need help, give me a call, and I'll be more than willing to help you. Okay. Let me see, what time is it? 9:03. Okay, let me see if I can squeeze in a solution for this problem. Now, in this case here, we're not dealing with a strong acid. We're dealing with a weak acid. And what you're going to find is that when it comes to weak acids, in order for you to find the pH values of those solutions, you can't assume 100% dissociation because it's weak, right? So basically, things are a bit more complicated. So I'm hoping I'll be able to do this problem in enough time for us to get to the end. So basically, you know what, I don't think I'll be able to complete. I'm just going to start it, all right? So basically, because it's a weak acid, I'm going to use HA to represent it, right? Now, weak acids undergo partial dissociation. What does that mean? That means that when you add the acid to water, only a small fraction of the molecules present will undergo dissociation, right? So if you could actually see the particles in the solution, you'll see mostly the undissociated molecules, right? The amount of the H plus and the A minus, or the conjugate base, will be relatively minute, right? So I'm going to use HA to represent the acid. So this is the dissociation that will take place. You're going to end up with H plus and A minus, right? So it's a system in equilibrium because you're going to have a back and forth, right? So therefore, we can write down an equilibrium expression for this, and that would be called the dissociation constant. Ka is equal to the concentration of H plus times the concentration of A minus divided by the concentration of HA, right? And according to the question here, that value for formic acid is 1.8 times 10 to the minus 4. So different acids, or I should say specifically, different weak acids will have different values of Ka, right? And in fact, so this is called dissociation constant. dissociation constant, right? And in fact, we can use the Ka values to make comparisons between weak acids. Basically, the larger the Ka value, or the larger the dissociation constant, the stronger the acid compared to others, right? If you have two acids that are weak, then the one with the larger Ka value would be the stronger of the two weak acids, right? Now, in this particular case, what we'd have to do is set up an ice table, right? So I'm just going to rewrite the equation here to give H plus and A minus. And then I'm going to set up the ice table. Initially, you're going to have 0.065. Here you're going to have 0. Here you're going to have 0. The change here, we don't know what it is. We're going to call the change in the concentration of HA minus X. So that means that over here, you're going to have plus X, and you're going to have plus X here. So at equilibrium, you're going to have 0.065 minus X. Here you're going to have X. Here you're going to have X. So therefore, we can write down that Ka is equal to the concentration of H plus at equilibrium, which is X times X, which is the concentration of A minus, divided by 0.065 minus X, and that would be equal to 1.8 times 10 to the minus 4. And what I'm going to do is stop right here, all right? And I'm going to continue from there to show you how to solve for X, because what you can do, which will work in some cases, is to make an assumption that X is small. And we're going to see what will happen as a result of that assumption. You'd expect X to be small because the acid is weak. You'd expect that the concentrations of H plus and A minus will be small, especially when compared to the initial concentration of the acid. Okay, so I'm going to stop here for today, and I'm going to continue solving this problem next class, all right? Because we certainly can't finish it now. All right. Any questions in the remaining 8 minutes? Any questions? Any questions? Okay, so if there are no questions, let me just check out here in Zoom. No questions out there in Zoom. All right, so that's pretty much it for today, folks. I'll see you guys next Monday. And for you guys out there in Zoom, I'm signing off now.